Um, Julia, thanks for the quick, efficient introduction. Again, my name is Brad Hartman, and the title is a little bit wordy, and I promise I had help making it wordy. Not a big fan of that, but I think it captures what we're talking about today. I just want to mention that a presentation really similar to this. I've given this internally to my company here at Jacobs, but I also shared this a couple of years ago, almost a year and a half ago at ASFPM's national conference in 2024. So that was a great opportunity to share some of my general experiences on this fish barrier removal program and some of the things that we at Jacobs and many others in the region of Western Washington are doing right now. I have included WashDOT's logo on here primarily because they are our client. They are our ultimate client that we're serving and helping right now with a lot of these barrier removals that have been mandated. So thank you, Julia, for inviting me, I guess, to present to your group today. I may not know many of you on the call, but it's my pleasure really to take some time and talk about some of my experiences. I also recognize that there's people probably on the call who have been involved in this program and probably know more than I do and have had different experiences. Just really quickly about me, I've worked 18 of the last 25 years, 10 years at CH2M before about 8 years ago, we were merged with Jacobs. And although I'm assigned to the Bellevue office there in Washington, I actually live in Salt Lake City, Utah. I finished my graduate studies at BYU in 2001, and yes, we were eliminated from the March Madness tournament, a couple of weeks ago or so, like most of us were. And then I've worked a lot across many Western states, and actually held an engineering license for about 15 years in the amazing province of Alberta, Canada. We did a large design build up there in 2008 to 2010 in the city of Edmonton. And then I also many years ago became credentialed with ASFPM for floodplain management. Most of my focus in my career, although I think we all get opportunities to do different things here and there, but most of my focus has been with H&H type of stuff, general drainage on highway and bridge, floodplain work with FEMA and others, and just general flood control. And I work in GIS a lot. And then for my company at Jacobs, I serve as a subject matter expert for a lot of bridge scour projects that we work on. The types of projects that I mentioned I work on span a lot of different things: highway, bridge, aviation, railroad. I belong to kind of a stream restoration group at present with a lot of wonderful professionals across a lot of diverse disciplines. And then I've been doing a lot of wildlife crossings lately, not just AOP or fish passage, but a lot of terrestrial like elk and deer and things like that. We're working on a project on Highway 20 in Skagit County right now, which has been very rewarding. Uh, just quickly, personally, I don't normally, I just thought it'd be fun to share some things that I like to do in my spare fun time. This is a picture of me just a few weeks ago in the South China Sea near Philippines. Really love the sport and experience of diving. And as I share some of these hobbies, if there's any new friends or buddies I can make on the call, I'd sure love to hear from you. This is my happy place in a little box with wheels. This is my little trailer I sometimes take up into the mountains, and it's something I've just enjoyed doing. When I was a little younger, I would backpack, and as I got older, I liked having a memory foam mattress and plumbing and heating and all that sort of stuff. I got into wristwatches a few years ago, and this is actually my dream watch. It's well outside my budget right now, but if anyone is a watch aficionado, I'd love to hear from you. And then I had another midlife crisis and got a new hobby of having collecting pocket knives, and just have really enjoyed that a lot. And then I had my last midlife crisis about a year and a half ago, and I bought myself a motorcycle. Never have I ever been on a motorcycle until I was 50 years old. And I took a class to learn how to work the dang thing, and it's been a lot of fun for me. This is actually a Royal Enfield for any of you who are motorcyclists. This has been a brand and a bike I've absolutely fell in love with. So that's just a little about me personally and professionally. I think what we're going to kind of talk about today is kind of the who, what, where, and when, and whys of fish passage in Washington. This is something that's been going on for decades, but has been accelerated in recent years. Um, our role at Jacobs, we've played a role on numerous crossings of our own, and working on some of the design and construction, the final design and construction of some of these crossings, and the bridge work and the highway work that's required. But we also had a role as a GEC Prime, which gave me and us an amazing opportunity to work with many amazing other partners and subconsultants there, and to learn a lot and to be exposed to different ways of thinking, different ideas, different expertise, and also to share what I could and what we can. Um, my role on the project, I before I actually relocated my official office to Washington, I was actually working on the program for about 2 years, and really I got a call one day where they needed some scour help. Many of these are bridges or large span culverts, and making them resilient and understanding the potential scour of the design life of the structure is important. And so I was pulled into it for that. I have a heavy hydraulics background, and so we've been working with a lot of modelers to make sure we have good numerical models put together so we can understand what we're doing and make good decisions with the stakeholders and co-managers. Again, this is just my perspective. Others who have been exposed to this work, and I've already seen a couple names on the call that I know who have, you will have different experiences. And if I, make a mistake and say something boneheaded, I apologize. Please call me and correct me. But this is just my experience on this program. I want to spend some time today just kind of showcasing what this looks like. And this is going to be a little mind-numbing for a few minutes, but I think some of these before and after pictures are extremely telling. And as I shared with other people, particularly outside of the state of Washington, who may not be aware of what is fish passage, or what are we doing here, or why are we doing it, or how much is this costing, I think this really drives home the perspective of what this really looks like when it's all said and done. We'll talk a little bit about innovation and resilience. We'll talk about floodplains a little bit. We'll mention the design processes and principles, and kind of start wrapping this up with flood risk, 2D modeling and scour, and then finalize with some of the challenges and opportunities that I've seen on this program and these projects. And then if there's time for questions, hopefully there isn't, I'm just kidding, I'll be happy to entertain questions. If I know the answer, I'll share it right away. If someone else knows the answer, please raise your hand and speak up. And if I need to go dig up the answer, I am very happy to do that. So again, just I guess if we're talking about the who in this sense, we've had these multiple species of salmon and these steelhead trout, which is a salmonid type of species where they reproduce and live in freshwater streams, but they also live and spend time out in the ocean, in the saltwater, and they return often to these streams and even the streams of nearby where they were born to swim upstream and to spawn and reproduce and make more salmon. And that's a good thing. That's a natural thing. That's what we need. And when they can do that and the streams are healthy, that's great. If we've got problems with the streams, they've got a problem. And kind of the why this is really, and this is a little bit dated, but it drives home the point that several of these different sea species and subspecies of salmon are really struggling. They're being listed in environmental in ESA lists. They're declining in population. Salmon are important for a number of reasons. They are a food source for human and many other species. It has a huge impact to the economy and to the Native American Indian tribes that are there in the region. There is just enormous cultural and tribal importance and tribal rights that they have to these fishing areas and to the species and fishing. So this is really just about saving them for dozens of reasons. The next why is why we're talking about this and why this is such an issue is because unfortunately, I guess over time, we as humans have created problems and barriers for the fish to do their thing and to go upstream and reproduce. And this is a little kind of a clever but illustrative cartoon illustration that WashDOT has produced that shows that there's multiple different types of barriers. They can be uh, too steep of slopes or high velocities that the fish and the juveniles just can't swim against. If we have barely any water, and I've seen some really sad pictures of these fish in their life cycle trying to swim in like an inch of water, that's like really, really sad. I've seen uh, drops on the outlet of some of these culverts that are higher than a foot or so, where the fish just can't jump up that, or the younger ones can't. If there's not enough headroom, if there's grates or bars that are preventing access, if there's other, and I'm just illustrating with the latter part of the list that there's other things that can produce a barrier to these fish. It could be a dam or a diversion structure. I know that's dams are that were built a long time ago are being addressed, and some of them are even being removed there in Washington and other states. It could be a water quality barrier. It could be a temperature barrier. It could be a levee. There's all sorts of different things that can provide access issues for these species. So again, just some of the numbers, and I think these are extremely telling. There's about 7,000 miles of just state routes and interstates in Washington. This is not including city and county roads. Um, you know, about 8,000 crossings in these roads that cross over water, and about half of those are considered to be fish-bearing streams. So we've got 4,000 crossings that should be conveying fish upstream and downstream. And of those 4,000, about half of those, so over 2,000, are considered to be documented barriers to fish. And almost all of those are culverts. And I know we can debate all day long about what a culvert is, but these are typically smaller diameter pipes that you'll see in some of the illustrative pictures I have that probably when these were put in conveyed expected flows, perhaps fine. But as time has marched on, as we've gained more understanding about habitat, they just are insufficient to be suitable for these fish. So just a little bit of history. There were a lot of treaties over the last century and court decisions early in this century. And in 2013, a legal injunction, a court order, required Washington state agencies like the DOT, WashDOT, or Department of Fish and Wildlife, Department of Natural Resources, and state parks to really accelerate correcting these barriers. And like I said, even in the 90s, Washington was aware of these and working to better understand them and removing them. And in this court order, the way I understand it is that there's about 1,000 of these crossings that have to be corrected that are included in what's termed as a case area or the injunction area. And by what year is it? 20, so 4 years from now, 90% of the habitat that was inaccessible has to be accessible and corrected by 4 years from now, 4 years from last month. That's what the injunction states. And that's about 400 barriers. So just less than half of the injunctions that are part of the case area. And this is a little bit dated again, but as of January of 2 years ago, about 150 of these have been completed. And that's only about 40% is what is needed. So since 2 years ago, many more of these have been corrected. And I think I was looking at the numbers the other day. But they're working very hard. They and us and many other people are working very hard to meet this deadline or to do the very best we can with the funding that's there. This is a very articulated process by WashDOT, and it's evolved over time. But these are dedicated, committed professionals at the department and all their consultant partners and the stakeholders and co-managers who are working very hard to do this the right way. And I mentioned all those groups just there. This number probably keeps changing and probably keeps going up, but this is about an $8 billion effort when all is said and done. So you can see that, the state legislature is probably very involved in trying to understand how they can earmark funds to do what they've been ordered to do. This is an interesting map. The yellow boundary you see here on the west side of the state is the case area that was in that 2013 court order injunction. And these red dots are the 2,100 documented fish passage barriers I referred to earlier. And you can just see the enormous density of those, especially in Northwest Washington, where you can see as they follow lines of key highways and roadways, and over and over and over as they're crossing streams that go from the highlands into these bays, sounds, and into the ocean, that there's just so many of these crossings. And again, about 1,000 of these, about half of these on the total map are need to be corrected pretty soon. This is a probably a slightly outdated map showing that since the mid-50s, 1950s, that is, how many have been corrected. So, the red dots on the previous slide were the bad news. These are the good news. We're making lots of progress and continuing to march forward and correcting these barriers. In 2024, I guess there were 390 as of 2023, I want to say. Yeah, that was the fish passage report of 2023. And in 1 year after that, there were 30 more. And then as of last, 2025 or the end of last year, there's been probably another 20 or 25 more corrected since then. So great progress. This slide is coming from, I think it's either WashDOT's website or Department of Fish and Wildlife, but it shows the case area again in yellow. And it shows all the barriers that are on the injunction list that need to be addressed. And those are shown in the hot colors, like the red, oranges, and yellows. And those are different based on the type of blockage it is. But then you see in the blue squares, the happy color, the cool colors, that many of these are being fixed and corrected as time has marched on. So this has been just really a fantastic thing. As far as the execution of the program, I just want to mention there is so much guidance from WashDOT, from the Department of Fish and Wildlife, from the State Aquatic Habitat ISPG guidelines in 2003. These are just 3 manuals that I have referred to and referenced to a lot, but there's just all sorts of guidance documents, all sorts of checklists, all sorts of workflows. It's updated fairly regularly so we can support clear direction and be nimble with new ideas, new innovation that's accepted as a good thing. Lots of training and communication is constantly occurring, and I'll refer to some of that through my presentation today. And again, just lots of people, lots of humans working together and trying to communicate the best they can to make a really good product at the end of the day. And there's, opinions will vary, and there's sometimes competing interests. But this has been a really wonderful project and program to work on for me. WashDOT has a couple of different design stages they refer to. They refer to them as the preliminary and final hydraulic designs, or typically a PhD and FHD. And these are planning level and design level documents that provide all the backup as to why and how we are producing a defensible design for what a crossing should be. And then, of course, design and construction plans are prepared following that. WashDOT actually requires people to have a fish passage certification to even work on these, or to be a principal author on some of these documents. And it's like 11 hours of videos, really good ones, and like a 50-question exam. So let's dive right into some kind of what this looks like. And again, maybe for some of you, this is old hat. For others, this is like, whoa, really? These are examples from, I think, 2022 and 2023. I've got probably a dozen and a half of these. I just want to walk through them because pictures are more fun than just me talking. But I mean, you're looking at, on the left side of your screen, a 36-inch culvert pipe that is completely sedimented in with, zero headroom, being turned into a 42-foot span bridge. And I mean, I just think these pictures are staggering and in a good way, to understand we are trying to restore the stream, floodplain, and habitat function. So these fish don't even know that they're swimming upstream or downstream and there's cars above them. I think that's really amazing. And I'll just point out some of these large trees, if you will, that are in the channel. I'll be talking about them a little bit more in the presentation, but those are on purpose and those are by design. Here's another example where they took a two-foot culvert and turned that into a 13 span, excuse me, box culvert made out of concrete. Again, pretty enormous root wads sitting there fairly close to the crossing. Another example, and these are not all small crossings, by the way. I think this one, I'm trying to remember this crossing where it was, but I think this was a slope or a velocity crossing, maybe a height. I can't remember. I apologize. But a triple 6x6, and then that turning into a single span over 208 feet. I mean, you can see all that vegetative fill material that all was removed and put into a fairly high crossing here, allowing that stream to be really fully restored all the way through. Pretty amazing before and after pictures in my opinion. A 5x5 box turned into two 44-foot span bridges. Again, you see some of that large wood that is placed and anchored even under the crossing because probably the amount of daylight and freeboard that's here. So pretty impressive before and after pictures there. Twin 2-foot concrete pipes turned into a 45-foot span bridge. Not the best of pictures, but just you can see what's going on there. I don't know if that's an oil slick down there that I'm looking at on the after picture. Almost a 6-foot corrugated metal pipe turned into a 29-foot span bridge, and a very tall one at that. Really interesting structure design and wall design there. So you can see the different disciplines that come in, not just people that are dealing with hydraulics, but people have to make this work in actual reality with the topography that's out there. Here's a squash pipe with a pretty decent span before that was turned into a 40-foot span bridge. In the after picture, this is from 2024. This is a 5-foot metal pipe that is turned into a much larger box culvert or bridge, if you want to call it that. And you can kind of see in this after picture that a lot of these areas are in urbanized places. They're not always in the middle of nowhere. They're very frequently not in the middle of nowhere. So we have to take into account, all the right of way and all the constraints we have for some of these crossing designs. Here's a 5-foot steel pipe that was turned into a 35-foot span bridge. Here is a 5-foot pipe that was turned into a 23-foot span bridge. And again, you can see some of that really large, those wood bowls that are even spanning the channel and have some, area underneath them. It's really interesting, the different unique designs that we're seeing in these crossings. This is a 3-foot pipe that was turned into a 116-foot span bridge. Again, all that wood there. And then a 2-foot pipe that was turned into a bridge again, considered a bridge because it's over 20 feet span per WSDOT, and then a 4-foot concrete box that is turned into a fairly good looking, very impressive arch span bridge. 4-foot corrugated steel pipe turned into a 26-foot span bridge. 30-inch RCP turned into a 19-foot culvert. You see some of those large boulders and pools and clusters there that were decided that they should be placed based, for the needed channel complexity and resilience. Then a 30-inch pipe turned into a 3-sided 16-foot span. A 3-foot concrete pipe turned into a 26-foot span bridge. I think we're getting towards the end here, but just bear with me as we just show a few more of these before and after pictures, which again I think are extremely interesting, not just from the layman's perspective, but just even from this community too. Here, this relatively small podunk 2-foot steel pipe turned into a substantial bridge here. So I think you get the idea of the before and after pictures. I think the next thing I want to show you is a time lapse that one of my good friends and colleagues at Jacobs, Gabe Ing, provided for me. I don't know exactly who gets the credit for setting it up and recording it, but this is pretty far upstream in North Washington State, across Squalicum Creek, and this is a creek that flows to Bellingham Bay along State Route 542. Probably many of you maybe live up there or have driven up there. But this is in August of 2023, and you can see here, beautiful area. You can see a big box culvert there in the bottom. I think these are 30-minute time lapses. And you can see here, I can't remember if it's the end of the month, might be the end of August, that box will just all of a sudden disappear as it goes away. I love the temperatures on the top right. There's Washington is so amazingly beautiful and cool in the summer, which is what I like. But you can see the temperatures as we get into August, September, and October, that these temperatures start dropping. So I apologize. I guess we're in early September. Maybe it was mid-September. This box starts to disappear, but they're working on the bridge structure in the background, and they're doing a lot of prep work. But here's we get, I think, towards the 15th of September, you'll see that box all of a sudden be removed, and they start working in the channel and start getting it prepared, and there it goes. So that's gone. They're doing the grading that the stream designers and the biologists felt was the right way, restoring that stream to what they think Mother Nature wants it to be. And you'll start seeing some revetment coming in, some large wood being staged and put in the channel and then put on the different sides. And there you see that coming in right there, just staged for right now. It's not a dam they're building. They're going to start putting that in different angles and orientations along the creek bed. But I mean, again, this is a fairly substantial bridge crossing, both span and height, compared to what was there before. So I think this is really amazing. It's going to stop and reset back to the beginning of the video here in just a second, but I wanted you to just see what this looked like now that we're in the 40 degrees temperature range. Okay, there you go. So that's back to the before. So I'm just watching the time here. We're okay. Just want to talk about very high level and generally speaking how this is done, and to remind you that we are trying to reconnect neighborhoods. As I work on more and more wildlife crossing projects, it's been seared in my brain that as we've developed as humans and built roads and bridges and neighborhoods and shopping centers, we are often cutting off habitat that both terrestrial animals and aquatic organisms and fish have been using for eons to move. And as we cut those off, you know, and again, I'm not a biologist, but it impacts their habitat. It impacts the herds and that are able to mingle and reproduce with each other. It starts impacting their DNA, and really they start fighting for survival and food and safe habitat and all those different things. So it's the same thing with fish. We're really reconnecting those neighborhoods that have been plugged and cut off for a long time. So we're not talking about fish ladders here. We're talking about restoring what Mother Nature thinks probably should be there if we can get inside her head the best we can. We are building in stream complexity. So if you go to a lot of streams, they don't look like concrete channels or flumes. We don't want an ecological desert where there's no imperfections, there's no scour holes to rest, there's no areas that fish can be protected from predators. We want to balance this out the best we can. And we want that floodplain function sometimes to even continue through the crossing. It's a different mindset where you might say, hydraulically speaking, I can get a 2-foot pipe, punch a hole through this roadway and get the design flow through the culvert without exceeding headwater limitations or meeting headwater requirements. But we're talking about more than water molecules here. We're talking about fish. And you know, having these floodplains be in as many areas as possible has all sorts of different functions and benefits that I didn't know before working on this project. I mean, it deals with the food chain, it deals with nutrients being built up and released, it deals with areas for change and room for the stream to move and meander and do what it will do over long periods of time. And so there's just lots of functions to floodplains other than just storing and conveying water. Oftentimes, we spend a lot of time in the field, and for those of you maybe on the call who've worked on these projects, probably know this. And we're spending a lot of time looking for what we term as reference reaches. We are looking for stable areas that are natural and consistent in the area of this stream, ideally, that gives us really good clues as to what Mother Nature wants for the stream. I had someone describe it to me as reading the land once, but we're trying to kind of put our calculations and our calculators and our computers in our back pocket for a minute and say, what should this look like? What does it look like upstream somewhere that is healthy? And can we do that? And again, we're looking at the geometry, we're looking at the slopes, we're looking at the floodplain and how wide the flow is at low flows. We're looking at the soil, sediment, and geology. We're looking at the vegetation. And we're looking at these channel complexities and habitat features. So in this picture, you see some timbers that are naturally fallen over the creek, or rocks that are jutting out, or areas that are vegetated and areas that are not, or sandbars, and these quote unquote imperfections that make this stream beautiful in Mother Nature's eyes and make it function, because this was formed over long periods of time, make it function in a healthy, ideally healthy way. And that's what we're looking for. Like I said, the answer is usually in the field, but we will get our calculators out and we will start looking at our best understanding of hydrology. What do some of the high flows look like? What do some of the low flows at bank flow elevations look like? And we're looking at USGS gauge stations. We're using computer programs like MGS Flood. We're doing the best we can. And then we start thinking to ourselves, what should this structure geometrically look like? Okay, it was a 2-foot pipe. Now what does it need to be? And sometimes we're changing the horizontal alignment. Sometimes we spend, well, not sometimes, all the time we spend a lot of effort in trying to figure out how wide does the crossing need to be. We know it was 18 inches before, but it probably needs to be about 18 feet now. And what does that cross section look like? Is it a V ditch? Is it a trapezoidal ditch? Are there benches? What are the side slopes? What should the freeboard be? We spend a lot of time looking at and designing a new stream bed material. We're going to be pulling out some of the stream bed material that's there now, and we're going to be putting stuff back in so that it is stable, resilient, it's functional, it matches, it's doing the things it needs to do. We're very careful about slopes. We're very careful about velocity and gleaning what we can from the hydraulic models. And of course, then we start looking at what channel complexity features, like those that large woody material you saw in those previous photographs. What do we want to put in there? And there's means and methods and ideas that all sorts of people have on this, and there's standard procedures for designing that. And I'll just mention kind of more into my world of things. We spend a lot of time developing two-dimensional hydraulic models, typically in SRH2D for DOT work, that helps us ask and answer all these what-if questions and iterate through different designs, and making sure that we think at the range of flows we expect over the long term, how is this channel performing in terms of shear stress and velocity and all these different things. And because in many cases we are uncorking these crossings, I just use that word, I have heard that word used before, but we're taking what might have backed up water before and might have even diverted water on the upstream end to some other place, but now we're opening that up. What does that mean for upstream and downstream? What does that mean for properties and structures and a habitat and everything else? So we're looking at those flood risks as well. I just want to mention here that we're looking also for resilience over the long term. I know that we consider sea level rise and tidal influences, but also we're looking at a wide range of flows all the way up through the 500-year, but also even what we expect in 54 years from now. What do we think the 2080 100-year or 1% flows would look like? And WDFW has a very helpful tool that for each of these documented crossings, someone has estimated that in 54 years, we estimate that at least in this case, the 100-year flow rate will increase or could increase by about 23% just due to climate change. And we run through these calculations both for the crossing design, but also scour on all of these crossings. I mentioned sea level and tidal influences before. And then going to, again, under the topic of resilience and innovation, talking about channel complexity. So again, you can see a bunch of professionals standing in this channel here, and looking and gazing on what they've designed, these large wood trunks with their root wads that are put in the channel at different angles, different locations, and they're anchored and bedded in so that they provide the complexity that these species appreciate. Again, we talk about mimicking what Mother Nature put there, sometimes what is called stream simulation. We're trying to simulate what this should be. We're wanting to be as natural as possible. We want to provide that floodplain function through the crossing, as I mentioned earlier. And, we want to do these things, especially where revegetation might be difficult. As an example of a channel complexity option that we have, one thing that one of my colleagues here at Jacobs, Dr. Tyler Foudy, has worked really hard on, working with WSDOT with studies and experimentation, is the meander bars. And they're still studying these things, and we use these often in some lower slope crossings to promote sinuosity and to help prevent the flows from entraining against the walls and just kind of sheet flowing all the way through. These usually are designed with organic slash at the heads of these structures that also rack additional material as time goes on. And they're also designed to be stable at high flows. The bar height, the top of these rock meander bars or lateral bars are you're typically set at like a 10-year flood flow elevation, but they are designed to be stable at high flows. Just a few other snippets from some of the design guidance that's out there. The picture on the right is a flume that Dr. Foudy had worked to create and test with WSDOT. But again, understanding that how these channel complexities work. And you can see in the pictures, you're going to have small little scour holes that we want to develop that are unavoidable and they're natural to develop at the heads of these at these structures. So just really great research and ideas that evolve as time goes on, but using the best available practices and the best available science and knowledge that we have at the time. And of course, we're learning. So I've mentioned large woody material several times. It is large. I think by definition, anything that is over 6 feet in length and 4 inches in diameter is considered large in this context. It typically involves the log, sometimes I think it's called a bowl, and the root wad together. It can provide, I should say, protection and stability for the creek. It also provides habitat. It lowers velocity. It produces scour pools for predator protection. For some of the smaller juveniles and younger fish. We include these typically in one form or another in all of our hydraulic models, and we'll refine the presence of these in our models as we finalize our models towards the end. We don't always put these below the roadway. It just depends on a lot of factors such as freeboard, but in these pictures as an illustration, you can see that they're put upstream and downstream of the crossing. And then the short crossing itself is they'll use other features. Again, these are designed with intent, and they're anchored down and ballasted and resisting buoyancy force and intended to be stable for high flows. Just a few other things, and again, I'm starting to get into areas that I'm not an expert in, but I think it's really fascinating of all the channel complexity tools and tricks that we have. So that would include small woody material, other names that they go by as slash and hog fuel. These are sometimes mixed in with the sediment or stream bed sediment for stability and different organic processes. Sometimes we use root wads without the trunk of the tree to have woody material in our crossings. They look pretty gnarly, and it's interesting to me, but I just find it fascinating with all that we're trying to do to use all the tools we have in nature to provide healthy crossings. Boulder clusters is another example that I've seen before used. And this is just kind of a screenshot. I don't remember which crossing this is. I apologize, across State Route 161. But you can see how on our preliminary and sometimes final design plans what these look like. In this case, we have plenty of large wood that is being shown upstream and downstream, within the limits of grading of the project. And then you see these lateral bars providing that sinuous stream flow at low flows inside the crossing. So I just think it's great to see these illustrative pictures. I want to talk a minute about these flood risk assessments. I know many of my colleagues have worked quite a bit on these, as have I. And this is a communication instrument that WashDOT requires so that we understand, hey, yeah, there's all this fish stuff we're dealing with, but we're also talking about water molecules here. So we got to figure that out. So whether these crossings are mapped by FEMA or not as a special flood hazard area, we are looking to identify early on, are we increasing any risks to public safety, to property, and are we meeting floodplain requirements, be it from the FEMA NFIP or any local jurisdictions like King County or any counties or cities on these new design crossings. So we are looking at impacts to the water surface elevation. We're looking at the inundation limits to the floodplain. We are looking for what that might mean for important features, typically downstream, in terms of property or structures. And really, like I mentioned, it's a communication tool to identify early additional permitting or strategies that we might undertake to protect life and property as well as the fish. So, can we achieve a no rise? Are we going to need a conditional letter of map revision? Can we adjust the design to minimize or reduce or even eliminate the impacts that we have? So that's really what this is. And we are almost always using an SRH 2D model. That is a model that was been put out by the Bureau of Reclamation a long time ago, and that in recent years, Federal Highways has adopted as kind of their tool of choice for highway, bridge, and roadway crossings. I only mention that because we're typically not using the regulatory model that FEMA might have used. So that presents some challenges because sometimes you're comparing apples to oranges, but we are usually comparing, we are often comparing pre-project and post-project right in the SRH 2D model, but also understanding what might be in the regulatory model analysis as well. We are using the 100-year flow, FEMA hydrology if available. If it's not, we're using what we come up with. And then there is close coordination between WashDOT and FEMA on this, as you might imagine. And it's a whole section of our reports. There's a whole section dedicated, and this itself, the FRA, is almost a report unto its own. This is on the screen. What I'm showing is just an example of an FRA exhibit. We are producing plan view figures. We are looking at this in cross-section. We're looking at this in profile. We're putting values on tables. And you can see this is across State Route 3 near Kinman Creek. And you can see in the aerial on the left that the red, let's see, how can I... let me do a laser pointer here. Here we go. You can see my bouncing ball. Okay, so the upstream end of the previously existing culvert, which was a 36-inch, was here in this red X. The downstream was there in that red X. So you can see a good example of how we have realigned the crossing a little bit more. And we're putting on some of these observation lines or BFE lines, and we're looking in the cool colors, the white to cool colors, areas where the water surface elevation has dropped as compared to between pre-project and post-project conditions. And then we're also looking sometimes in these reds, oranges, and yellows in the hot colors of where water surface elevations might have been increased. Typically those are limited areas, typically downstream, even though these are typically steady state hydraulic models that we're doing. By opening up this crossing, it just changes the whole hydraulics of the site. You can also see in green hatch, these are areas that were previously inundated that now have become dry. So you can see some of that backwater on the upstream end that's no longer there. And then on the downstream end, you can see some areas that are now flowing with some depth of water that weren't before. And again, the corresponding cross sections and tables. And again, it becomes challenging because you can see some of the stark differences. I mean, sometimes we're changing the whole stream bed. We're not just building a Costco or a Walmart in the floodplain and saying, hey, how did this impact us? We're changing the whole stream. So we're just trying to understand what that looks like. And so these FRAs are a great point and mechanism to do that, even prior to ever getting to a permitting document like a CLOMR or a LOMR. This is kind of the area where I've spent most of my time or a lot of my time rather, is the modeling. Again, we're using SRH 2D. I have a quote up here by George Box, which reminds all of us that, these models are not perfect. They are our best mathematical approximation of physical processes, and we're trying to make them as useful as we can to understand and predict what will happen with our proposed designs. And as I worked with many great people over the last four plus years, we have some amazing modelers and some great people across 30 plus companies that are exercising their judgment, doing their part to restore some of these crossings. And we at Jacob spend a lot of time teaching and mentoring and helping people follow best practices for this two-dimensional modeling. And it includes, how are we developing good terrains for use in the model? And do we have a good computational mesh? And are we understanding the Manning-Zen values correctly? And how are we modeling channel complexities? And then just numerical stability and dealing with tides and really making meaningful comparisons and meaningful predictions as to what our crossing should look like. And again, WashDOT has recently rolled out a certification requirement. It's like a 3 or 4 day course taken through the National Highways Institute that requires people to work on modeling for these crossings. So a lot going on. And then also the other major role I've played is in scour. We are always trying to understand the total maximum scour to be expected over the lifetime of the structure, both long-term vertical incision, but also if the flows are being constricted, and typically they're not. Typically we're opening them up, but that mechanical scour and again with climate change. So we're just trying to understand how to protect the bridge as a DOT asset after we've done all we can for the fish. And it's a very complex topic. There's constant ongoing advances and direction that we're coming up with. It requires some experience. And one thing I'll just say here is, if you read HEC 18, and that's kind of Federal Highways' master Bible document for bridge scour, it's often within the context of we are going to constrain and constrict and contract this flow. We are going to build some abutments and some embankment, and we're going to put in some economical pipe or culvert or bridge, but the flow is going to have to squeeze through this. And in many of these crossings, it's just the opposite. We're opening up the channel a little bit more, and there really isn't a contraction, but we still have to do our due diligence to make sure we understand the potential total maximum scour that could occur in some of these streams. It really is dependent on the quality of the hydraulic model. It requires coordination with geologists and geotechnical staff. And also WashDOT has a training and certification process for this that requires about 60 hours for an individual to sit through and then take an exam. So I think I'm just watching the time, got about 9 minutes left. Let me try to kind of wrap up here. I'm just looking at the leftover slides. We're nearly the end. Just wanted to talk about challenges and opportunities here. And I've mentioned it already. No one side is the same. These are like your children if you have kids. They're all completely different. They have different reference reaches, different levels of urbanization. I've seen some of these crossings go underneath hotels. I've seen some of these crossings be highly constrained. Some of these crossings are extremely long and extremely steep. And I mentioned this one in red just because I thought it was worth highlighting and mentioning more poignantly, is that this legal injunction requires DOT and Department of Fish and Wildlife to repair state barriers. Sometimes we will spend lots and lots of money to repair a state barrier, which is A, we should do it, and B, we are ordered by federal courts to do it. But right upstream or right downstream, there'll be other barriers to fish passage. It might be a city or a county road. It might be a private culvert or a private road or something like that. And I believe all of those will have to comply with law in future years. And so it can seem really frustrating or counterproductive to say I had to fix this state barrier, and now the fish have another 20 or 30 meters of habitat, but right at that point there's another barrier that when that gets corrected, they'll have another 400 meters of habitat to gain access to. So it's going to take a long time. It's going to take a lot of intention and a lot of money and a lot of people coming together and doing the right things. And as I've mentioned, this is very multidisciplinary. I mean, I've I'm hobnobbing with biologists, fluvial geomorphologists, other H&H folks and designers and surveyors and other people who have interest and stake in the stream health and heavy civil engineering disciplines, and of course geologists as well. So there's lots of people that have to come together really well for all the right reasons and do all the right things in the right time. I mentioned designing channel complexity is always not straightforward, but it's an iterative process requiring thought. I mentioned already the flood regulation complexities of dealing with outdated mapping or changed topography or opening up these crossings. There's ongoing changes sometimes in training that is appropriate to keep the quality high. And I didn't mention this yet, but sometimes we get into what we call retrofits or performance management situations where we designed the best crossing we could, and we are heavily monitoring these crossings in the weeks, months, years following construction completion. But we might find out that something went awry, something didn't work, something got damaged, some erosion occurred that we didn't expect. And so WashDOT, I think by the injunction and by practice, are watching these crossings for quite a bit of time after they're constructed. And we've had a few of these experience some failure in some form, and we've gone in to do these retrofits. So this is a learning experience for all of us. WashDOT has some great tools and resources online. This is just one of their websites where you can learn more about the science and technology and best practices of fish passage. So just kind of in summary, this is my last slide, and we can open it up to any questions if there are any, and hopefully I can answer them. But this has been described as a moonshot effort. I think it's really appropriate that right now we've got the Artemis 2 capsule barreling on back, to the Earth after going into space farther than humankind has ever gone before. And the pace at which we are going here has never been done by any other DOT, to repair literally decades of disruption to fish. There's many disciplines involved. That's a good thing generally. We're trying to provide long-lasting habitat that will work for these fish. So in decades, if not centuries down the road, our kids and kids will be grateful that we did this. We're looking at flood risk. And again, this is a highly organized effort that does allow for innovation, however, and the learning and the improvement and the adaptation will just continue. The best things are yet to come. And I just want to give a shout out to our Jacobs Seattle-based ecosystem and stream restoration team. They're absolutely amazing. And I say that with all due respect to all the amazing people that are working in this industry all over the country and especially in the state of Washington. So that is the end of my presentation. I am happy to try to field questions. And if I don't know the answer, as I've